So, welcome to another exciting digital design class. We've got a homework 7, which is due tonight. It's on the 2's complement. And I was wondering if there were any leftover questions on homework 7. Going once? Going twice? Number 10. Number 10. Let's see what we got. Excuse me while I find my cursor. Oh dear. Mouse is non-responsive. Sorry. Number 10. Number 10. Well, number 10. Actually, number 10 is a very good question because number 10 asks, what is that thing, that component with the question mark in it? And I like this question very much because what it makes you do is look in the book. So if you read the book, you can see there it is. That's the component that's missing, and it's in page 250, and that is figure 5.8 on the 4-bit adder subtractor. The only difference between this diagram and the one in the question is that we're using a exclusive OR instead of a 2-to-1 multiplexer in order to choose between B and B inverse. And the reason why it works is because if you take the output here, this part, B just goes out as is, and this becomes B. But if you take the input and you make it an M, if you make M equal 1, then what happens is 1 and 0 becomes 1. 1 or exclusive OR with 1 becomes 0. And so this is B inverse. And so you can use a simple exclusive OR. This is M exclusive OR B in order to be able to invert a variable. So all you have to do is assert the input to be 0 if you don't want to invert it, or assert it to be 1 if you do want to invert it. And that's why that works. And you have to, well, complement and increment the accumulator, CIA, in order to be able to perform the 2's complement. So that's that. That was question number 10, which, by the way, is also on the midterm, which we'll talk about after we're done with homework 7. Are there any other questions for homework 7? Number 5. Number 5. Number 5. What is the output for an 8x8 multiplier if the input is I just sworn I just did this. Yes, I did just do this. That's how you do that. So you'd write out the stuff and then the rules. 1 times 1 is 1. Anything times 0 is 0, including 0 times 0. So 0 times all of this is 0, 0, 0. 0 times all of this is 0, 0, 0. But the only difference is you got to shift it over by 1, just like regular multiplication. Then you take this and you copy that and put it right there. Take this, copy that, and then shift it. Take this, copy it, and shift it again, because you got 3 1s, so you do 3 rows that way. And then you got 2 zeros, so here's the 2 zeros, and then you got a 1, which is all the way over to the end. Then you do your addition, and that gives you an answer. Was that too fast? Okay. So just in case someone is tuning in late, that was the answer to question 5. And you'll see questions like this on the midterm as well. Any other questions about homework number 7? Going once? Going twice? Number 12. Number 12. So number 12 is interesting. Number 12 is a thermionic diode, which consists of a filament in a vacuum with a plate. This is called a hot cathode, and that differentiates itself from a device that has a separate cathode. That would be called a cold cathode. Here we're using the filament itself as the cathode. And so what we can do is we can have conductivity in only one direction, and it has a schematic depiction that looks like this. And so this is an interesting device because it uses connectors which look just like light bulb connectors, and that's what they are. A21 screw thread light bulb connectors, because Edison had light bulbs all over the place, and so people just used it. And they call these Edison sockets. So this tube has 2 Edison sockets at either end, which is kind of cool, actually. And the question is, what kind of voltage drop can we expect between the anode and the cathode? Well, that's a very fine question. Sir Ambrose Fleming worked as a consultant for Samuel Morse. He wanted to help refine the transatlantic telegraph so that it could be more sensitive. And so he created a device, which he patented in 1904, that had a very low voltage drop. And to this day, we don't know what that voltage drop will be. It's a how would you call it, material property of the vacuum inside the tube, and also a property of the distances away from the anode and the cathode. So there's no way to know from the given information. And so this could be a very sensitive device, perhaps much more sensitive than the semiconductors of the day. Well, I don't know if they had semiconductors that day, but anyways, this was how they did it, and that became the dawn of the electronic era, because soon thereafter, Orion sought to modulate the voltage between the anode and the cathode using, this has 2 parts, they call it a diode because it has 2 parts. Add the grid and it becomes a triode. And the triode, or Orion tube, essentially can act either as a switch or an amplifier, modulating the power that flows from the cathode to the anode. So that's the answer. There is no way to know from the given information, and that is for question 12. Can't know. Can't know. Any questions about that? This is an interesting device, right? Because it represents the dawn of the electronic era. Once you had the amplifier and the electronic switch, you could create electronic digital computers. And in fact, the first ones were made with vacuum tubes. Any other questions about homework 7? Going once? Going twice? Question 22 and 23. Oh, you want a twofer? Wow, we have to charge double for that. Let's see. 22. What is the 8-bit 2's complement of the decimal number minus 100? decimal number, base 10. Well, if it's the 2's complement of a negative number, then it's probably going to be a positive number. So what they're really asking for is the 8-bit representation of decimal quantity 100. I can convert that to binary with repeated division. And that comes to and that be that. And that's a correct answer. So that's 22. Any questions about what I just did? No questions? Hearing none, I shall proceed to 23. What is the 8-bit 2's complement of the decimal number 100? Well, now we're looking to take this number and form the 2's complement. So now we're going to get negative 100. So to form the 2's complement, form the 1's complement, then I add 1. 1 plus 1 is 0, carry 1, plus 1 is 0, carry 1, that's 1, 1, 1, 0, 0, 1. Base 2 equals minus 100, base 10. And that is a correct answer. What do you think of that one? Good, right? So one... Sure. The question is, what is the 8-bit 2's complement of the decimal number 100? So if we're going to find the 2's complement of the decimal number 100, we start with the positive number 100, and then we find the 2's complement by finding the 1's complement, which means we invert, and then adding 1 to get the 2's complement. And that's 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. The 1 comes down over here. This 1, this 0, that 0, that 1. And that gives you an answer. That's the, that is negative 100 in base 2, using 2's complement. Who got confused by that? Did I go too fast? You speak up if I have. I'll do it again. Did you understand about the repeated division, right? Everybody got this part. Yeah, okay. Yeah. So all I did was, I hope I didn't take too many shortcuts. I formed a complement, which is here, and then I added 1, because I have to do CIA. I have to complement and increment the accumulator. So there's the complement, and here's the increment, and I add 1 to all of this, and that gives me negative 100. So is that all right? Yeah? Good, good. Certainly. So let's see now. Question 27. What is the 4-bit binary number of the 2's complement of You know, I'm reading this and thinking critically. I should probably, what is the 4-bit binary number of? I should probably reword that to make it more clear. So to find the 2's complement of a 4-bit binary number, you form the 1's complement and then you add 1. And the 1's complement is you take the 0 and you make it into a 1. You take the 1, you make it into a 0. and then that's your 1's complement. And now you add 1, and 1 plus 1 is equal to 0. Carry the 1. There's the 1, 0, and a 1. And so that is equal to the base 2 version of, this was 6, so this will be minus 6, base 10. Is that correct? Yes, and that is a correct answer. That's the answer. I get 100. Actually, I should get more than that. I should get extra credit. But hey, I made up the test, so it's not fair. What else? Any other questions about homework 7? This is due tonight, midnight. Be there or be square. Okay, I'm hearing no questions. Going once? Going twice? 3 times. I am now declaring homework 7 is done. Yay! Homework 7, yay. We did enough homework 7 there. Next thing up. Oh, let's have a discussion about the midterm. That's always fun. I came up with a midterm, which is now available to you on Blackboard. It is due. Midterm is due on the 29th. That is 3/29, 21. That is a Monday, 2 weeks from now. So you have 2 weeks. Open book, open notes. And you can open the midterm, you can print it out, you can look at it offline, you can take note of individual questions that are difficult, you can ask about them in class. I will cover some midterm questions for you. I can't do them all because, why can't he do them all? Because it's big, I guess, is the answer. How big is it? Well, it's big, big, big. Let's see. I'm just looking now. Just the midterm. Just the midterm. And then you will be off the hook for your Easter break. So let's see. There's 69 questions here, so it's unlikely I'll be able to do them all. You can be selective about which ones you find challenging, and I can cover them in class for you. And I can even start doing that now. But what I would do is, instead of immediately diving into the midterm review, is just sort of give you a little brief overview of how this course is proceeding. So the course consists of essentially 2 parts. The first part, which we'll have finished at the end of this midterm, is on combinational logic. So combinational logic is, generally speaking, logic that can be computed in 3 gate delays. And what I did was I made a little overview of the course so you can see what's going on. So this is essentially the whole thing. This is the course. Here's the course right through in 2 parts. And so this part right in through here, this is the part we're going to wrap up when we're finished with the midterm. So this is combinational logic. Everything can be done in 3 gate delays, and a gate delay is the worst delay you get from AND, here's AND, or an inversion. So it would be represented in this way: AND, or, and inversion. Right, I don't know which delays will be the worst because I don't know which logic we'll be using, but in effect, if we know how long 3 gate delays are, we can effectively compute anything in those 3 gate delays, and they could be measured in nanoseconds. And if you went to the stock room and went into the back and got dog breath TTL logic that we have there, it's nanoseconds, tens of nanoseconds. It's a very fast computation. So much faster than you would need for most applications. So that's the combinational logic part. Then the next half of the course is what we'll call sequential logic. That takes longer, much longer than 3 gate delays. Could take a lot longer than 3 gate delays. And then we can do counters, we can do finite state machines, we can do computer architecture. All of that is something we've been preparing for by doing the combinational logic. And that is how the course will proceed. And then what I have here is kind of like this list of topics that we will see in the midterm, and which, because it's a comprehensive midterm, which we have seen in the course. So we'll look at things like base conversion, like base 8 to base 10, or base 2 to base 8. We'll look at things like 2's complement, which of course we've seen extensively here in homework 7. We'll look at the Boolean laws. If you can't do the time, don't do the crime. Wonder if the Boolean police will get me. And then we'll do simplifications, and that's also done with Boolean algebraic manipulation. We'll do canonical forms, product of sums and sums of products. We'll have questions about K-maps, 3-variable K-maps, 4-variable K-maps, no 5-variable K-maps, no 6-variable K-maps. We'll have don't cares included, so that'll be in the test. You'll see that. There's multiplexers and demultiplexers, or also known as encoders and decoders. It's the same thing. We'll have some questions about tubes, vacuum tubes, light-emitting diodes, rectifiers, adders, multipliers, subtractors. We'll have questions about how to build large multiplexers from little multiplexers. And we'll have questions about various numbering systems, including 2's complement, 1's complement, and sign and magnitude. And that basically covers everything in the midterm in a sort of a broad topic approach. Right? This is the sort of the topics you'll see on the midterm. And no surprises. Everything is pretty much stuff that you've seen already. Midterm is a mashup of a lot of prior homeworks. When I do 69 questions, it's kind of tedious to type them all original questions, so I'll borrow a lot from the old questions. So you'll have seen everything, but you still may want to, go over stuff because maybe you don't remember, and it's kind of hard to remember because there's a lot of material. So that's the bird's eye lowdown on the midterm caper, and the course for that matter. Any questions about any of this? So the midterm, you get 2 stabs at it. You get graded by computer, and you'll get the highest of the 2 grades. The average point allocation for the 1.5 for the 69 questions is 1.5 points per question. All the same, no questions. Even some questions are harder than others, no doubt, but you get the same number of points for every question. No penalization for guessing, unless you guess wrong, then you get no points. And don't be late, because Blackboard is brutal when it comes to lateness. And then someone says, I unconsciously joined your earlier session, so I don't think I need to sit through the same class again. Is this okay with you? Absolutely. Absolutely. If anybody wants to come to the earlier session, you don't have to go to the 2 sessions. That's fine. As long as you've got your questions answered, that's fine. That's fine. So, any people don't need my permission to switch sections. I don't care. I'm here anyway. And so that's that. That's the midterm. And what I'll do, since you have access to it now and you can open it, is I will open the floor to questions about the midterm. And if there's any specific question you'd like me to cover in the midterm, I would be happy to do so. How's that for being a nice guy? Yeah. Yeah, no, it's midnight on Monday, the 29th. So you got 2 weeks. 2 weeks. Oh, don't wait till the last minute on this one. That doesn't pay, because you know what'll happen. You lose power. I lost power last night. It was what a nightmare. Couldn't even zap a cup of coffee. They browned out the microwave. It couldn't make it through a cycle of a minute. And everything was beeping. All the UPSs woke me up. Yeah, so don't wait till the last minute for that stuff. And who knows what'll happen to computers and that sort of thing. It's all so unreliable. What else? Oh, so if there are any questions about the midterm that you'd like me to cover, I would be very happy to do that. Got the midterm open now. So maybe I'll ask you guys a question then. I'll try one of these questions out of the midterm. Here's a question. Question number 1. Let's start with question 1. Question 1. Convert 158 base 8 to base 10. How do I do that? Alvin, what should I do here? Yeah, Alvin, are you with us? Yep, that's correct. We call it positional notation. So it's 8 times 8 to the 0 plus 5 times 8 to the 1 plus 1 times 8 to the 2. And that is equal to, well, let's see, 8 times 8 is 64. And this is 40. And then this is 1, so that's 8. And now I have 104 plus 8, which is 100 and... no. Did I do this wrong? I'm getting a calculator out just to make sure. So I'll make sure my answer key is right. 5 times 8 is 40 plus 64. 104 plus... oh, that's supposed to be a 3. Shh, I was wondering, why doesn't it work? Plus 3. Yep. So that's 107. I was like, geez, it doesn't work. Holy mackerel. But that should say 153. Somehow I wrote it down wrong. If you write the question down wrong, the answer will be wrong. So, yeah, got to write down the right question. I was going to say, how come that doesn't work? I'm sitting here with a calculator going, that doesn't add up. So that's that should be a 3. 3 times 1 is 3. There. That's better. 4 plus 3 is 7. Yep, every day of the week. Yep. So what do you think? Got any questions for me? Questions out of the midterm? Well, if you don't have any questions about the midterm, I'll just do new material. Won't that be fun? Let's try. Number 30. Number 30. Which of the following binary multiplications are correct? It says here that it's 1, 1, 0, 1 times 1, 0, 1, 1. What does that look like? So that looks like a correct answer to me. What do you think of that? Does everybody understand how the multiplication works where you're shifting over? I'm using graph paper here because I like to keep things sort of organized and lined up, because it's very easy to kind of make a mess of things, and if you do this on unlined on paper, it's not going to do you any favors. So neatness counts when it comes to this kind of thing. Sure, sure. So let's see now. Let me go through it again. Let's do this. One gets down here. This one just comes down. And you have this one. I'm sorry, I got lost. This is given in the question. And this is given in the question. And he wants to know if this is if the binary multiplication is correct. So I did the binary multiplication and I got this answer. And the answer is yes, indeed, that's a correct answer. So these are given in question 30. It's one of the possible choices. Another one that it gave us is 1, 1, 1, 0, 1, 0, 0, 0. And if you multiply this, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and then it's 0, 1, 1, 1. And then when you add it, which is not the answer that they provide, so that is an incorrect answer. So you can eliminate that one. You can go to the next one and you'll find out it's also incorrect, but the first one that I just did is correct, and that is a correct answer. Don't know if that answered your question. I got confused about the ones in your question. You don't have to. I mean, if you've got a... did I answer your question? Here? Down here? I'm going to number these. 1, 2, 3, 4, 5, 6, 7. What row are you on? Okay, so this row, right in through here, right? Okay. Because of carries. I'm just carrying. Yeah, so these are carries that came from prior stages, and sometimes what happens is you have 1 plus 1 plus 1, and you get 1, carry the 1, and then you have to keep adding the carries in, so I wrote the carries out. I don't know if that answered your question. I could do the addition again if you like, and you'll see it. But in any case, 1, 0, 1, 1, that's from here, and then you're going to have 1, 0, 1, 1, that's from here, and then you're going to have zeros, that's over in here, and then you're going to have 1, 0, 1, 1, that's over there, and then you have 1 carries in 1, 1, 1 plus 1 plus 1 is 1, carry the 1. And then that 1 comes, should have come in somewhere. Oh, 1 plus 1 is 0, carry the 1, and here's that carry right there. And then you have 1 plus 1 is 0, carry the 1, here's another carry right in through here. 1 plus 1 is equal to 0, carry the 1, and there's the extra 1. So if you're you know, following along with the addition, you could see the carries are being written here. I suppose I could have used a separate color or something. Or I could redo this if you like. Should I redo it? I can redo it. Here. All right? We're going to do multiplication. All right? So that's 1, 0, 1, 1, 1, 0, 1, 1, 0, 0, 0, 0, 1, 0, 1, 1. Okay? Now, let's change the color. It's a totally different color. So that's 1, 1, 1. 1 plus 1 plus 1 is 1, carry the 1. You can see why I'm writing a 1 there, right? 1 plus 1 is equal to 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. And that 1 comes right down and through here. And so now you can see the little green, yeah, I probably should have done this in a different color to begin with, but now you can see the little green stuff is matching the other thingy. Does that help? Yeah, it's easier to see it when you change colors. And so that's how you do that kind of multiplication. And that is a correct answer for the for question 30. That's question 30. Any other questions about this midterm? I'm sure there are. So I'll ask you a question then. Here, let's try and do 33. Here's 33. The pointy-haired manager decided that he needed a 32 to 1 multiplexer. But the only thing he gave you to build it with was 4 to 1 multiplexers. He's got a lot of them. He has infinite 4 to 1 multiplexers. Infinite. But how are you, as a digital design student, going to construct a 32 to 1 multiplexer with 4 to 1 multiplexers? What should I do? That sounds like a plan. Since each 4 to 1 multiplexer has 4 inputs and 1 output, if I have 8 of them in my first stage, then I will have 0 through 7, that is 8 different outputs, but I'll have 32 inputs. And then, how many do I need for the next stage? 4 inputs per multiplexer, so I gotta have 2. So that's 2 right in here, and they've got 2 outputs. So how many do I need for the next stage? Just 1 4-to-1 multiplexer, and I'll use half of it. And that's going to give me an output F. So how many multiplexers do I need? 8 plus 2 is 10, plus 1 is 11. So I need 11 4-to-1 multiplexers. 11, 1, 1, base 10. 11 4-to-1 multiplexers in order to make a 32-to-1 multiplexer. 11 packages. And all because the pointy-haired manager got a real deal from his buddy who he plays golf with and makes 4-to-1 multiplexers. He says he sells them to you really cheap. In fact, he practically gives them to you. He's got a whole golf bag full of 4-to-1 multiplexers. He takes them with him to the green. He's got a real chip on his shoulder. Get it? See what I did there? Chip on the shoulder? Ah, boy. Okay. Yep. Digital design humor. So let's see. Any other questions about the midterm? You probably can't stop laughing because of the chip on the shoulder joke, right? Yep, very, very funny. Okay, so maybe I should ask you guys another question. How about this? Question number... I know. Here's a good one. F of x, y, z equals z. Given f of x, y, z equals z, find the canonical sum of products. How do I do that? Let's see. Brianna, how do I do that? Well, suppose I said we had to make a truth table. And X, Y, Z, and I'll just do the truth table. I'll number it here for you. I think I did that right. I'll number this too. Now, what should I write for F? There you go. And so then, what would the F equal M, well, I guess it would be sigma M of? What do I put in this part? There you go. That's it. You do know how to do this. And that is one of the questions. Which one, I don't know. It's one of these questions. Let's see. I don't know which question that is, but that, you know, question 13. That's possible. Question 13. Yep. Well, it's close. Question 13 is close. With question 13, it said f is equal to y instead of z, which changes things somewhat. I don't know if there... I may have misremembered it. It probably was y. But changing it to y doesn't really change the basic idea of how you approach the problem. Let's try... Oh, here's a good one. Let's try question 12. I'm picking these at random. F equals sigma m of 0, 2, 4, 6. What does f prime equal? And it looks like you got to do it either in canonical sum of products or canonical product of sums. So let's start with canonical sum of products. And it says here, yeah, what do I write in here? Anybody know? Let's try someone. Daniel? What do you think? That sounds good, but I don't see that here. That's not available. Well, what if I wanted to write it in pi product form? That is canonical product of sums. What would I write? Brendan, what do you think? No, 1357, that's for the sum of products. For the product of sums, it's 2, 4, 6 for the, well, for the inverse. Yeah, so that would be available to us as one of the possible solutions, and so that's the one I would go with for number 12. So you kind of have to, I don't know, think back to chapter 2 or something like this at the beginning of the semester. That's a pain, right? Because why do professors do these things? Well, presumably you learned it once, but then you forgot, and now if we use a comprehensive midterm and or comprehensive final, it puts it into long-term memory, where long-term memory is defined as over the summer, so you can remember it for digital design 2 or the computer architecture class or something. It's not like you're going to remember it forever. Let's see, what else? Anybody want to ask a question? I'm not going to torture you with two's complement questions because you guys have seen those already. Sort of scanning through. Here's one. Well, that's sort of silly. This is silly. Here, find the minimal sum of products. Oh, I like that. 15. Given the following K-map. colors. Looks like a color. How's that for a K-map? Given the following K-map, find the minimum sum of products. Other color here. No, I had another color. I had green. Oh, here's my green. Okay, so what shall we loop? Jason. Jason Rosales, are you there? Yeah. So we'll loop these two right in through here, and what do we call that one, Jason? There you go. And what do we do about this column over here? There you go. That is correct. And now what do we call it? Yep, B prime. So now I have A prime or B prime equals F. And that is a correct answer for 15. See what an easy test this is? So easy. I should have made this harder. But I figured 69 questions. That'll keep you busy. It'll keep you out of the bars. Let's see. What else? So that's got a few more K-map questions here. I think you guys will figure them out. Well, here's one. Question number 17. We'll do 17. Question number 17. So it's a K-map, just like the K-maps you're used to. Now, given the following K-map, find the minimum product of sums instead of the minimum sum of products. Oh no, it's so tricky. What do I do? Somebody help me. It's time to call on someone new. Let's see. Carson. I don't think I've called on you lately. Carson, what do you think? Carson Swope, are you there? Gotta unmute yourself. Alrighty, how about Riley? Riley Fitzsimmons, are you with us? How about Mateo? Oh, who's speaking up? Okay. What shall we do? It did? Yeah, I see that. What's going on? Just a minute, please. I'm having a technical problem. There, is it back? What happened here? I don't know what's going on. Oh dear. I may have to. If I stop share, it says your screen share is paused. Stop share, and now share screen, and now see if that worked. Yes. Oh, all right. Yeah, you got to unmute. So, would you like to help me? How do I find the minimum product of sums? That is right. That's right. So, what do I loop? All right. And what do we call the green loop? It's the video is frozen, you mean? No, I stopped. I waited for you. You don't see the green? Oh, shoot. What's going on? I may have to do a stop sharing. Oh, it says your screen share is paused again. Stop share. Why is this happening? Share screen. Is it working now? Yeah, it says you are screen sharing. Before it said screen sharing is paused. I don't know why. So anyways, the bird's eye lowdown on the green loop caper. Can you give me a product term for that? So B is changing, but C is not changing. Good. And A, C prime. Or, and then let's do the brown loop right in through here. What would that be called? AB. And then what about the black loop? Yes, B, C prime. And that would be, since you've circled the zeros, F prime. But what I'd like to do is get F in minimum product of sums form. How do I do that? Yeah, yes, De Morgan's theorem. So you get this, and this, and this. Whoops. And that's a minimum product of sums. And it is the correct answer because I'm looking at the answer key. So that is correct. What do you think? So is it bringing everything? You know, it's not something that you do every day, and you can forget this stuff. But with minimum product of sums, when you circle the zeros, you're getting a minimum sum of products for F prime. But when you want to get the minimum product of sums, just use De Morgan's theorem on the minimum sum of products, and you will get F, the non-inverted version, and you'll get the product terms. And that becomes a minimum product of sums. This is a minimum sum of products for f prime. So you're basically getting a minimum sum of products for f prime, then use De Morgan's theorem to get the minimum product of sums. That's the procedure. Got it? Is it anyone confused by this? I think it was a while since we've done it, so it wasn't necessarily something that you guys remembered. You know, here's another one you probably don't remember. Don't cares. I'll do a quick don't care example just in case you guys have forgotten this stuff. So we'll make this the don't care. We'll make this the don't care. And these are all the ones. Probably ought to use a different color. These are all the ones. And then this is the zeros. The zeros. Oh, what do I loop? What do I loop? Habby Bool. Are you with me, Habby? Habby Bool? What do I loop, Habby Bool? Yeah, let's... 4 ones. What should I loop? Just give me the numbers. Got it. Do I have to loop this one? Okay. And then what do we call this brown loop in here? That's it. And that's how you loop with the don't cares. And so the minimal form on this one is B. And that is the answer to 18. What an easy midterm. Thank you, Professor Lyon, for giving us an easy midterm. Yeah, isn't that nice? Wow, what a nice guy. All right. No sense beating around the bush. Everybody should go to Rate My Professor and say how wonderful. Yeah, no, it's cool. It's cool. So, yeah, go to Rate My Professor, and I can use it to get my merit pay or something. So there's, yeah, what do we call this? A 4-variable K-map here. And it's got don't cares, so I might as well do an example with don't cares and a 4-variable K-map because this one has a little bit of a trick to it. Let's see, A, B, C, D, 0, 0, 0, 1, 1, 1, 1, 0. You know, I sort of remember taking this class when I was a student, and I struggled. I mean, really, it was a lot to learn. So I remember this was not easy. If I make it look easy, it's just because I've been doing it for a little while. Now, let's see if we can put in the don't cares. Don't cares. And then we'll put in the ones and zeros. I'm changing colors. Let's see, these are zeros. There's a 0, and there's more zeros, and all the rest are 1. Oh, there's more zeros, and that's 1. And this is question number 19, as you can see. So, what do I loop? Anybody want to chime in? Sure, that's a good one. What do you call that loop? Sounds good. What else can I loop? All the corners. Yes, all the corners. That's the key on all the corners. And what would you call that loop? B prime, D prime is correct. So that is the answer to, well, interestingly enough, the answer F equals B prime D prime or BD does not appear, and therefore none of the above is the correct selection for 19. None of the above, because none of them look like that. So that's I don't know. Is that tricky because it's none of the above? Maybe. I don't know. I didn't mean it to be tricky, but you kind of have to know. And the same K-map appears later, but then it does give you one of the answers that's correct, and that's B prime D prime. BD. So this does appear in this does appear as a correct answer for 20. So this is actually 2. You're getting a twofer. So it's also 20. So it's none of the above for 19, but this is the correct answer for 20. Because it's the same exact K-map, only the answer appears. Let's see. K-maps. Diodes, multiplication. You guys tell me, what do you want me to cover? I got a few minutes left. Number 21, let me do that. Oh, it's another K-map. Okay. I think this may be... Here, to another piece of paper. So this is number 21. Let's change colors. So it's don't cares right down the center, and then more don't cares, and then all ones over in here, and then some zeros, and then it says select the minimal form for the given K-map. Looks like it's going to be a minimal sum of products. What shall we loop? Here comes the train. I missed it. I always miss that train. Or maybe, more to the point, it misses me. Like this. Okay, and what do you call that product term? Yeah, that's it. That's the answer. So that's 21. An easy one. Did you need any of those don't cares? I don't think so. Looping them would not have given you a more minimal form, that's for sure. So F equals A, that's just a wire. Can't get simpler than that. That's really minimal. Any other questions you'd like me to cover? I think we might have time for one more. It's already, well, actually, it's already 3:11 and fraction. So we got 3.5 minutes maybe. Any questions? Well, hearing none, what I'll do is I'll say this. Please take a look at the midterm and bring your questions with you to class on Thursday. And if you don't bring any questions, then I'll feel at liberty to do new material. Therefore, bring questions. And enjoy the rest of the day. Stay bundled up. It's cold out, but nice and clear. And stay safe, and thank you for your attention. Thank you. Thank you.